Good morning. Myself, K. Ravikumar, Associate Professor, Department of Pharmaceutical Chemistry, School of Pharmacy, Nalla Narasimha Reddy Education Society, Group of Institutions. So today I'm going to explain about phenols. The objectives of today's class. The students at the end of the class, the students able to write the structures and nomenclature of various phenols. Students able to explain the properties like boiling point uh, and solubility of phenols, and the acidity of phenols can be explained by the students. Coming to the topic, phenols are aromatic compounds which contain one or more group of hydroxy groups directly attached to the aromatic ring. So these are aromatic compounds which contain one or more hydroxy groups attached to the aromatic ring directly. It may be attached to the phenyl group, it may be attached to the naphthyl, any. So they are the simplest derivatives of family called as phenols. Phenol differ from alcohols. What is the difference between phenols and alcohols? Alcohols are the compounds which contain hydroxy group directly attached to the aliphatic chain or cycle. Whereas in phenols, it is an aromatic ring. The hydroxy group is attached directly to the aromatic ring where there is a delocalization of electrons. Electrons are moving from one carbon to other carbon. There is a delocalization in aromatic ring. So hydroxy groups are attached to the aromatic ring, whereas in alcohols, the hydroxy group is attached to an aliphatic chain or alicyclic compound ring. The simplest phenol is called as C6H5OH. We call it as phenol. It is also called as carbonic acid. According to the nomenclature of phenol, the hydroxy group is used as a prefix and benzene part is used as a suffix. For example, phenol are named as hydroxy compounds where this phenol is called as hydroxy benzene, where hydroxy group is acting as a added as a prefix and benzene is added as a suffix. There are a few other examples here where we can name this is a phenol part and the nitro group is attached to the para position. We call as para nitrophenol or 4-nitrophenol. If we have two or more nitro groups on this, we need to consider the position of your main functional group. When you consider hydroxy group and nitro group, hydroxy group should be given highest preference. So numbering starts from here and numbering should be done such that the numbers should be getting least possible number. So 1, 2, 3, 4. At second position and fourth position, you have nitro groups 2,4-dinitrophenol. So here this is a chlorophenol or 2-chlorophenol or orthochlorophenol. So this molecule, it is a orthomethylphenol, commonly called as cresol. There are some common names for molecules. So compound containing hydroxy group and methyl group on the aromatic ring, we call it as orthocresol. If they are at meta position, we call it as metacresol. Para position, we call it as paracresol. When naming phenols that contain carboxyl groups or carbonyl group, functional group, so that hydroxy group becomes a substituent, we need to add a prefix called as hydroxy, because the functional group carboxyl group or carbonyl group will be given highest priority than that of hydroxy. So hydroxy group becomes the substituent. For example, if you take this molecule, we can't call it as phenols because carboxy group is taking priority. So it is a benzoic acid and hydroxy group is present at the third position, because 1, 2, 3 meta position you have hydroxy group. So meta hydroxybenzene. So aldehyde is also a priority given functional group than that of hydroxy group. So it is a benzaldehyde, benzene with aldehyde group. So 4 position you have hydroxy group, it is 4 hydroxy benzaldehyde. When phenols contain more number of hydroxy group, we need to add di or tri as a prefix. So if we have two hydroxy group ortho to each other, we call it as dihydroxy, ortho dihydroxybenzene, which is commonly called as catechol. If hydroxy groups are present on the meta position to each other, we call it as resorcinol, or M-dihydroxyphenol, commonly called as resorcinol. If the two hydroxy groups are present at 1 and 4th position, we call it as para-dihydroxybenzene, para-dihydroxybenzene, then it is hydrophenol. So orthohydroxybenzene, metahydroxybenzene, and para-hydroxybenzene, all these three are isomers. If we have 3 hydroxy groups, then we call it as 1, 2, 3 benzene triol, because it is you can even write 1, 2, 3 trihydroxybenzene, or benzene triol, because you have 3 hydroxy groups, we call it as triol, and commonly called as pyrogalal. Alkyl phenyl ethers are also called as alkoxybenzenes. So in this molecule, the methoxybenzene is acting as substituent. So methoxy group with benzene we called as methoxybenzene, commonly called as anisole. Ethoxybenzene we call as phenetol. If you take the example of this molecule, so sometimes phenoxy group is also acting as a substituent. So C6H5O is acting as a substituent because you have alkyl group as a number of carbons more than 7, more than 6. So this main nucleus is acting as a alkyl group. Aliphatic chain is acting as a main nucleus. So 1, 2, 3, 4, 5, 6, 7 remembered carbon, and the phenoxy group is acting as substituent. At third carbon you have phenoxy group, and fourth carbon you have chlorine, because you need to number like this in this from this carbon. If you number from this carbon, it becomes 1, 2, 3, 4, 4 chloro and 5 phenoxy. So we need to give we need to get the cumulative least number. So it is 3 phenoxy, 4 chloro. That is alphabetical order P and P chloro. Chlorine comes first. Chloro 4 chloro 3 phenoxy heptane. So compounds which contain hydroxy group in the side chain. So this is not an aromatic alcohol or phenols, because this hydroxy group is not directly attached to aromatic nucleus. It is attached to a side chain. So such compounds are called as aromatic alcohols, but not phenols. So it is a benzyl alcohol. Benzyl alcohol, it is not a phenol. It is a aromatic alcohols. Similarly, this molecule benzene is attached to two aliphatic chain, that is ethyl group and alcohol, it is ethanol. So phenyl is attached to the second carbon, we call it as 2-phenyl ethanol. Coming to the physical properties, most of the phenols are liquids in nature. The simplest phenol is liquid, but most of the compounds are low melting solids. Most of the phenols are low melting solids. Boiling point of phenols are higher than aliphatic alcohols. Why boiling point of phenols are higher than alcohols? Because in phenols there is a aromatic ring and there is a delocalization of electrons. That is the reason phenols are having a higher boiling point than of aliphatic alcohols, in which aliphatic alcohol there is no resonance, so there is no delocalization. So the attracting or binding, formation of hydrogen bonding will be more in phenols. So the strength of the hydrogen bonding will be more. It needs high temperature, high energy to break that bond. So when you compare the boiling point of phenols along with other alcohols, see here molecular weight, they are having same almost similar molecular weight, phenol 94, 100 and 102, whereas boiling point is drastically increased for phenol, that is 182, whereas cyclohexanol, it is alicyclic alcohol, it is 162, and hexanol, it is the aliphatic chain alcohol, it is 157. So the boiling point of phenols is higher than that of comparatively other alcohols, aliphatic alcohols. The solubility also, solubility of phenol is more in water. Only the once phenol, starting phenol is having high solubility, whereas most of the other phenols are having insoluble in water comparatively, because the substituents may affect the solubility of phenols. Isomers have varied boiling points. So we come to the isomers. If we take the example of paranitrophenol, metanitrophenol, and orthonitrophenol, the boiling point varies because orthonitrophenol have low boiling point than other para and meta isomers. Why? Because paranitrophenol and metanitrophenol can form intermolecular hydrogen bonding, whereas orthonitrophenol can form only intramolecular hydrogen bonding. That is the reason paranitrophenol is having 279 boiling point, whereas orthonitrophenol is having 216. You see, meta and para have a very high boiling points because there is two molecules have intermolecular hydrogen bonding takes place. Because of that, there is a strength increases between these, so it needs high temperature to break this intermolecular hydrogen bonding. Whereas coming to the solubility, their solubility in water is due to hydrogen bonding with the water molecules. If you see the solubility para group, there is a hydrogen bonding with water molecules. That is the reason the hydrogen bonding needs a lot of energy to break down. So the solubility increases. Even interaction with this functional group with water increases. The more interaction with water molecules, the more the solubility. So phenol is having more solubility in the water. Intermolecular hydrogen bonding, if you take the example of intermolecular hydrogen bonding, the vapor pressure decreases, and so that steam distillation also decreases. So boiling point increases. Coming to the orthonitrophenol, the functional groups are very near to each other. There is a form, the proximity between the oxygen and hydrogen are very near, so that there is interaction between these two and form intramolecular hydrogen bonding. So this molecule is not interacting with the water. So that is now intermolecular hydrogen bonding is not taking place in orthonitrophenol. So the vapor pressure increases, boiling point decreases. So it leads to volatility. The volatility of orthonitrophenol increases and boiling point decreases. Coming to the another property of phenol, phenols are can form salt very easily, because whenever phenols are having a good property called as acidity, phenols whenever they are treated with water, it forms a salt. It forms a salt. So whenever the phenols are treated with aqueous hydroxy groups, it forms salts. So phenols, when normally they are insoluble in water, which are acidic in nature, when they are treated with base try to abstract this proton. So it forms a phenoxide ion. Phenoxide is a stable ion which is forming a salt, that is sodium hydroxide. Sodium phenoxide is formed, which is soluble in water. So phenols are having a salt formation property. Whenever phenols are treated, phenoxide ions are treated with mineral acids like HCl, again the phenols are formed. Acidity of phenols are very important because phenols are more acidic than alcohols. We compare acidity of phenols with alcohols. Phenols are much more acidic than alcohols, but they are less compared to carboxylic acid or carbonic acids. Why? Because phenols are having a stable phenoxide ion in aqueous solutions compared to alcohols. Alcohols, so phenols, whenever treated with OH, it forms a stable phenoxide ion. So whenever phenol is treated with OH, then it forms a phenoxide ion. Phenoxide ion, which is there, it can form easily stable ion. Why? Because this phenol O- will have tendency to donate the electrons to this aromatic nucleus. Why? Because aromatic nucleus is acting as withdrawing group. This carbon, aromatic carbon, is acting as a sp2 hybridization. So the electron withdrawing capability increases. so that oxygen's electron cloud is being withdrawn by this aromatic ring. So this O minus negative charge will be contributed to the aromatic ring. So when it donates here, then there is that involves in the resonance. So the pair of electrons is donated to form aromatic nucleus to form double bond. The already double bond which is there will shift to the next carbon to form O minus, and negative charge is formed. That will not sit idle. It try to delocalize to the next carbon. When it delocalizes, the para carbon gets negative charge, and further when it is under further delocalization, this carbon gets negative charge. So here, whatever the loss of hydrogen, oxygen negative charge is donated to the aromatic ring, so that delocalization take place. That is the reason phenoxide ion is more stable than that of phenol. So phenols are more acidic than that of alcohols. But phenols are converted into their salts, converted into their salts by aqueous hydroxy groups, but not bicarbonates. Whereas carboxylic acids can can react with bicarbonates to form salts. Because carboxylic acids are very strong acids, they can lose a proton very effectively to form carboxylates or carboxylates ions. But phenols are not having that tendency to lose proton with the bicarbonates, because bicarbonates, aqueous bicarbonates are less basic, whereas aqueous hydroxy groups are strong base. So that is the reason phenols do not react with sodium bicarbonates to form phenoxide ion. So the reaction is not backward. But whenever phenoxide anion is there, when it is reacted with a strong acid, that is carbonic acid, then there is a formation of phenols. So salts are converted into free phenols by aqueous mineral acid, carboxylic acids, or carbonic acids. So if you see the acidity of phenols in terms of pKa, we know that pKa value is very important. It can be used to know the acidity of phenols. So phenols are having a pKa value of 10, which are stronger acids than water, which is having a pKa value of approximately 15. So considerably weaker acid than carboxylic acid. Carboxylic acid are stronger acid than phenols because carboxylic acid is having a pKa value of 5. So when you compare here, the more the pK value, less the acidity, less the pK value, more acidity. Although they are weaker than carboxylic acids, but phenols are stronger acidic than alcohols. Why stronger acidic than alcohols? We'll see. But if you see the pK value of alcohols are 16 to 17, whereas pK value of phenols are only 10. So when you compare here, the lower the pK value, stronger the acids. So phenols are more stronger acids than of alcohols, right? Why phenols are alcohols are less acidic than that of aromatic alcohols? We'll see. Though how hydroxy group attached to aromatic ring are more acidic than that of hydroxy group attached to alkyl group. Means normal alcohols are less acidic than that of phenols. Why it is so? So when you see the resonance hybrid structures, then we'll know why phenols are more acidic in nature. If you see the alcohol ROH, when it is treated with when it undergoes ionization, it gives alkoxide ion. So here the delocalization is not there. Only one single structure is formed. There is no multiple structures. So resonance hybrids are not formed. So alcohol and alkoxide ions are represented in a single structure. Whereas when you see the phenols or phenoxide ions which contain benzene ring, they are we know that they are hybrids of capillary structure. So they are producing resonance hybrid structures. If you see here, phenols, we know that they are resonance hybrid structures. When they undergo ionization, they forms phenoxide ion. So here the rings are capillary structures. So we can represent in this format. So the phenols undergoes ionization to form phenoxide ion. The structure are similar. So the resonance stabilization, both the molecules and the ions in the same extent. So because of the resonance stabilization, the molecules have less energy. Because of low energy on each of the structures, there is no difference in energy content in the molecules. So acidity of phenols is about same as that of alcohols. If you see this structure, OH and OH is converted to O minus, O minus, there is no difference in acidity. But when you see in other additional structures, there is a delocalization of electrons takes place. Means oxygen being more basic in nature, that is trying to pull the electron cloud, that is trying to donate, share the pair of electrons, share the pair of electrons to the aromatic nucleus. So when it is sharing the electrons to the aromatic nucleus, I told you already, this carbon is undergoing sp2 hybridization, and because of that, so sp2 hybridized carbon will try to pull the electron cloud from oxygen. So the lone pair of electrons which are there will try to donate to the aromatic ring, so undergo delocalization. We know that. So the ortho, para, and ortho positions will have negative charge in phenol, whereas in phenoxide ion, also the negative charge is present at the ortho, para, and ortho, para, and ortho positions. But when you compare these structures, observe the positive charge is there in phenol, whereas in phenoxide ion there is no positive charge, only negative charge is present. So whenever there is positive charge and negative charge in the structures, the potential energy of the molecule increases, because there is a attraction, there is a energy required to force the positive and negative charges. So there is a energy requirement. So potential energy of this phenol increases, whereas in the phenoxide ion there is no positive charge, only negative charge is present. So potential energy of the molecule is more less. So less the potential energy, more stable. When you compare phenol and phenoxide ion, there is the phenoxide ion is more stable. When phenoxide is more stable, it loses the proton very fastly, and acidity is more. That is the reason phenols are more acidic than that of phenoxide alcohols, alkoxide ion. So phenols are having both positive and negative charges. Phenoxide carries only negative charges. So energy is supplied for opposite charges, and the potential energy increases. Phenol is having more amount of energy, whereas phenoxide is having less energy. So definitely phenol is less stable in that of phenoxide structure. If you see the resonant energy structure here, when you see the alcohol when it undergoes ionization, it requires amount of energy to form alkoxide ion. The potential energy is less. But when you compare here aromatic alcohols, there is a delocalization, there is a resonance stabilization here, and also for the phenoxide ion also. But when it undergoes ionization, this energy is more stable, resonance stable than that of phenol. So comparatively, phenols are stronger acids than that of alcohols. So in the summary, what we have discussed is we have seen the structure of phenols, its nomenclature of phenols, and the properties, boiling point. Why boiling point of phenols are more? Because it forms hydrogen bonding, and solubility of phenols undergoes hydrogen bonding and solubility increases, and phenols are more acidic than that of aromatic aliphatic alcohols, because in phenols there is a delocalization of electrons takes place, resonance takes place, whereas in phenol alcohols, alkoxide ion, there is no delocalization of electrons. That is the reason phenols are more acidic than that of alcohols, but less acidic than that of carboxylic acids. Why? Because in phenols, the charge is delocalized over the aromatic nucleus. It requires a lot of distance to delocalize the electrons, whereas in carboxylic acid, C double bond OO, the oxygen which are available, they lose the proton very effectively, and resonance is more stabilized. So carboxylic acids are very, very stronger acids than that of phenols. With this, we'll conclude the class. In the next class, we'll see how the substituents will affect the acidity of phenols. Thank you. The references we have referred is Aaron Ball, and Marcet Boyd, and IL Phenol. Thank you.